This is section 9.5, Inscribed Angles. We begin with a definition of what an inscribed angle is. An inscribed angle is an angle whose vertex is on a circle and whose sides contain chords of the circle. So the vertex has to be on the circle. The sides of the angle must contain chords of the circle. That means the sides must go through the circle. In the first picture there, the blue circle, angle 1 is an inscribed angle because angle 1 has its vertex on the circle right here. It's on the circle, and the sides are such that they contain chords of the circle. They cross through the circle. Number 2 is also an inscribed angle. Vertex is on the circle, the sides contain chords of the circle. Number 3 is not an inscribed angle. While its vertex is on the circle, this side is not a chord of the circle. So the angle 3 is not an inscribed angle. So inscribed angles give us now a second type of angle in a circle. Previously we saw a central angle whose vertex was the center of the circle. An inscribed angle is any angle whose vertex is on the circle, so on the circle itself, and whose sides contain chords of the circle. An inscribed angle intercepts the arc on the interior of the angle. So the arc that is the interior of the angle, this arc for angle number 1, is the arc that the angle intercepts. This arc, which happens to be the major arc here because it's the biggest one, is the arc that angle 2 intercepts. So the arc that's on the interior of the angle is the one that we say the angle intercepts. Okay, let's use that in this theorem. The measure of an inscribed angle is equal to half the measure of its intercepted arc. The measure of an inscribed angle is half the measure of its intercepted arc. So in number 1 here, if this arc was 40 degrees, then angle 1 would be half of 40 degrees, which would be 20 degrees. In number 2, if that arc is 300 degrees, angle 2 would be 150 degrees. The measure of the inscribed angle is half of its intercepted arc. Proving this theorem requires looking at 3 different cases, and I've drawn each of the 3 cases for you, case 1, case 2, and case 3. Notice point B is the same in all the cases. What's different is whether the ray BC, the chord BC, whether that goes through the center of the circle, whether it is to the right of the center of the circle or to the left of the center of the circle. We are just going to write down the key steps to proving the case 1 of it. We might do case 2 and 3 in class. So for case 1, one of the sides of the angle is a diameter of the circle. It goes through the center of the circle. So first what we're going to do, in our first step in the proof, these are just the key steps, so I'm not going to write it down as a formal proof. So I'm just going to draw radius. The radius I'm going to draw is the one from the center O to A. I'm going to draw radius OA. And I'm going to call angle ABC X. ABC will be X, and I'm going to draw OA. So let me draw it now. Okay. So that's just setting up what we're going to do. So now I know angle A is also going to be X. Why is angle A going to be X if angle B is X? Because the radii of the circle are equal in length. So this triangle we have here is an isosceles triangle. So by the isosceles triangle theorem, those angles are equal since the sides opposite them are equal. Okay, so angle A is X. Now, angle AOC is an exterior angle to that triangle. And if you remember way back from last semester, an exterior angle is equal in measure to the sum of the two remote interior angles. Angle AOC is going to be angle A plus angle ABC. It's going to be x plus x, which is 2x. Okay, the measure of an exterior angle is the sum of the two remote interior angles. That was the theorem we had last semester. Okay, so if angle AOC is 2x, angle AOC is what kind of an angle of that circle? It's a central angle. Very good. And a central angle is equal to the measure of its arc. So arc AC equals 2x. The reason for that is simply the definition of the measure of a minor arc. We defined the minor arc to be the measure of its central angle. So by definition, that's true. But angle ABC was x, so that means arc AC equals 2 times the measure of angle ABC, which means angle ABC is half of arc AC, which is what we wanted to prove. That's what this theorem was claiming, that the measure of an inscribed angle, in this case angle ABC, is half the measure of its intercepted arc, which here is arc AC. So case 1 uses the fact that one of the sides of the angles was a diameter of the circle. It goes through the center, therefore we can set up a central angle. We would use case 1 to prove cases 2 and 3. We would draw a diameter from point B, and we'd sort of split up our angle into 2 pieces, and we'd add them together. Here's an example of how we'll use this theorem. Find the values of x and y in circle O. So you'll see the blue angle that I've drawn with its vertex at S, that's an inscribed angle with a measure of 50 degrees. The pink angle I've drawn with its vertex at T is an inscribed angle whose measure is x. So let's find x. Well, x is going to be half the measure of arc PQ. That's its intercepted arc. But arc PQ is 40. X is going to be half of 40 degrees, which is 20 degrees. Okay, x is an inscribed angle. Its measure is half of its intercepted arc. Angle S is 50 degrees. So angle S, which is 50 degrees, is half of arc PR. But arc PR is 40 degrees plus y. So this is how we're going to find y. We're going to take this equation that 50 equals 1/2 of 40 plus y, and we're going to solve that for y. First we need to multiply both sides by 2 to get rid of that 1/2. So 100 is 40 plus y, which means y is going to be 100 minus 40, or 60 degrees. So both of those use their theorem that the measure of an inscribed angle is equal to the measure of its, or half of the measure of its intercepted arc. There are 3 corollaries to that theorem. Corollaries, remember, are things that are easy to prove from a given theorem. The first one says if 2 inscribed angles intercept the same arc, then the angles are congruent. Well, if the measure of each of those angles is half of the arc, then each of those angles is half of the same arc, so those angles have to be congruent. That's pretty simple and common sense. So in this picture I've drawn angle 1 and angle 2 intercept the same arc. So angle 1 is congruent to angle 2. Second corollary says an angle inscribed in a semicircle is a right angle. An angle inscribed in a semicircle is a right angle, which makes sense because if it's inscribed in a semicircle, then it's equal to half of the measure of that semicircle. So angle L is going to be half of 180 degrees. Half of 180 degrees is 90 degrees. So it's a right angle. So that makes sense. An angle inscribed in a semicircle must be a right angle. Angle L must be a right angle. And then the third corollary says if a quadrilateral is inscribed in a circle, then its opposite angles are supplementary. So we've inscribed a quadrilateral, which means all 4 vertices of the quadrilateral are on the circle, and the sides are chords of the circle. Then its opposite angles are supplementary. So angle H plus angle F is 180 degrees because those are supplementary, and angle E plus angle G is 180 degrees because those are supplementary. Notice this is just a generic quadrilateral. It's not necessarily any kind of parallelogram or a trapezoid or a kite. It's just a 4-sided polygon that's inscribed in our circle. And that forces the opposite angles to be supplementary, which would not be true about any generic quadrilateral that's not inscribed in a circle. Here's an example of how to use these things. Find the following. Let's first find x. X is the measure of angle ACB. Well, x is an inscribed angle, and it intercepts arc AB up here. Okay, so x is going to be half the measure of that arc. But notice angle ADB, which is 40 degrees, also intercepts that arc. Angles that intercept the same arc are congruent. So x is 40 degrees. If you don't see that, realize that angle ADB is 40 degrees, so that makes the arc 80 degrees. So x is half of that, which makes it 40 degrees. Angles that intercept the same arc are congruent. Angle ABC, well, point O is the center of the circle, so AC is the diameter. That means arc ABC is a semicircle. So angle ABC must be a right angle, must be 90 degrees. Arcs that intersect a semicircle are right angles. And angle BAD, well, we've got a quadrilateral. ABCD is an inscribed quadrilateral. So its opposite angles must be supplementary. So angle BAD plus angle BCD, which is x plus 30, must equal 180 degrees. The opposite angles, this and this, added together must be supplementary. They must be 180 degrees. But we know x is 40 degrees. So we've got 40 and 30 makes 70. Angle BAD plus the 70 must be 180. It means angle BAD must be 180 minus 70, or 110 degrees. And one final theorem. The measure of an angle formed by a chord and a tangent, so not 2 chords, is equal to half the measure of the intercepted arc. An inscribed angle is formed by essentially 2 chords. This is an angle formed by a chord and a tangent. And we don't have a name for that kind of an angle, but it turns out that its measure behaves the same way as the measure of an inscribed angle. The measure is equal to half the measure of the intercepted arc, just like an inscribed angle was. So in my very first examples, I had this angle 3 over here. Angle 3 is an angle formed by a chord and a tangent. And so that angle is also half the measure of its intercepted arc, even though it's not an inscribed angle. So for example, if this arc over here is 220 degrees, then this arc over here must be 360 minus that, and 360 minus 220 is 140. So this arc is 140 degrees, which means angle ATP is half of 140, which makes it 70 degrees. And here are your immediate practice problems. If point O is the center of each circle below in number 1 and number 2, find the values of x, y, and z. So in number 1, you end up with a triangle there, an isosceles triangle. Use that to help you figure out the other angles of the triangle and then their arcs, which will be double the angles, because the angles are inscribed angles, so they're half of the arcs. In number 2, you don't have a triangle, but you've got angle x, which is an inscribed angle, so it's half of its intercepted arc. Use that, and y is the central angle, and then you can find z. And that is the end of section 9.5, though make sure you draw these pictures.